When an application crashes under heavy traffic, the user volume is rarely the cause. It fails because the architecture handles the wrong kind of growth. When a system starts to slow down, the default instinct for most developers is to throw money at the problem. They buy a stronger single machine by upgrading the CPU, the central processing unit, and increasing the RAM, which is its short-term workspace memory. This approach is called vertical scaling. Imagine you run a busy restaurant. To serve more customers, you don't build a second kitchen. You just hire one singular, hyper-fast super chef and expect them to chop, cook, and plate everything at superhuman speeds. It is a tempting strategy. It is cheap, simple to manage, and powers the back end of almost every early-stage startup. But it contains a strict physical ceiling. Consider what happens when an app goes viral and traffic spikes 10 times higher than normal in a matter of minutes. The hardware immediately hits its limits. The CPU maxes out at 100% capacity trying to calculate operations, and the RAM completely overflows with queued user requests. Your super chef is overwhelmed, drops all the plates, and the kitchen halts. Because everything runs on one machine, the entire application goes offline for every single user simultaneously. At this level of demand, money stops being the solution. There is no physical server on Earth large enough to handle infinite global scale. Surviving hypergrowth requires abandoning the single machine mindset entirely. You have to change the physical layout of your architecture well before the crushing wave of traffic arrives. The necessary evolution is horizontal scaling. Returning to our restaurant, instead of relying on one super chef, you open multiple identical kitchens and divide the incoming orders among them. This diagram shows a load balancer at work. A load balancer is a routing device that intercepts incoming user traffic and distributes those requests evenly across multiple server nodes. Distributing the load removes the physical ceiling of a single machine. If traffic doubles, you simply add more servers to handle the weight. But there is a massive catch. Managing one machine is easy. Managing hundreds requires them to talk to each other, introducing massive communication complexity. Adding more machines solves your hardware limitations, but it immediately trades them for a new operational headache. You have survived the physical crush, only to enter the nightmare of distributed complexity. To understand why distributed systems break, we have to look at stateful design. In a stateful system, a server relies on its own internal memory to remember a user's session data and past actions. In a single server setup, that works fine. But in a horizontally scaled system, it is fatal. If you log in on server A and the load balancer routes your next click to server B has no idea who you are. This diagram illustrates stateless design, the mandatory rule for distributed systems. Instead of storing data internally, the server processes the request and instantly offloads the data to a separate external database. The server acts with intentional amnesia. It handles your request, sends the data away, and immediately forgets you ever existed. Because the servers hold no personal memory, the routing problem vanishes. Any machine in the network can step in, grab your context from the external database, and serve your next request seamlessly. Horizontal scaling is physically impossible without this architecture. The servers must be entirely stateless, forcing the external database to act as the single authoritative source of truth. A common beginner mistake is assuming you must build this massive, horizontally scaled network before you even acquire your first 100 users. A system does not fail everywhere at once. It fails at its bottleneck. A bottleneck is the single weakest point of constraint in an architecture, usually the database, where failure will inevitably start. Instead of blindly upgrading the entire infrastructure, senior engineers hunt for this specific constraint. They identify exactly what part of the system takes the longest or gets hit the most, and they optimize only that component. They also build in graceful degradation. Graceful degradation is an engineering safety net, where a system under extreme stress intentionally disables non-critical features, like search indexing or heavy analytics, to ensure core functions stay online. Scalability isn't about preventing stress entirely. It's about designing a structure that bends, isolates weak points, and survives under immense pressure instead of shattering. The most effective path to scale is evolutionary. You start simple with vertical scaling on a single machine, but you structure your code to be strictly stateless from day one. Sustainable architecture requires building a foundation that is flexible enough that your early decisions don't trap your future growth. Systems fail when they grow with the wrong assumptions. And while keeping your servers stateless solves the routing problem, it pushes all the pressure onto the database. Next time, we'll look at how to identify the silent data bottlenecks that kill performance before you even notice them.